Hi, welcome back to AP Chemistry. You're here with Mrs. Mays and we are studying equilibrium. Today we're going to focus on the reaction quotient. The reaction quotient is the result that we get when reactant and product partial pressures or concentrations are substituted into the equilibrium expression. Then we can use Q to determine how the concentration or the pressures need to be adjusted in order to reach equilibrium. So basically what we do is we compare Q to K. So if Q is equal to K, then we know that the system is at equilibrium and there will be no net change. Where Q is greater than K, then the forward reaction, let's write an equilibrium expression to help us. So we have products over reactants. So if Q is too big, then that means that the numerator is too big and we have to get rid of those products. That means the reverse reaction predominates and we will shift towards reactants or towards the left to reach equilibrium. On the other hand, where Q is less than K, then that means that the forward reaction predominates, because if Q is too small, then we have to get the denominator to increase so that overall the value goes higher, and that means we will shift towards the right to reach equilibrium. Here's an example of how we might use this. The equilibrium constant is given as 0.09000 at 25 degrees for the reaction of water with dichlorine monoxide. And we want to know for which of the situations is the system at equilibrium. And so I have a couple of different scenarios: situation A, situation B, and situation C. We'll evaluate each of those separately to see which system is at equilibrium, and for those which are not at equilibrium, what direction will they shift so we can get to equilibrium. Let's start with situation A. First, we'll write the equilibrium expression for our Kp value. So we have products over reactants. So that's the pressure of HOCl, hypochlorous acid, or HOCl as we like to say in class, and that's raised to the second power, all over the pressure of water, vapor pressure, right, multiplied by the pressure of dichlorine monoxide. So we know that when we're at equilibrium, that works out to be 0.09000. But we're given conditions that we're not sure if it's equilibrium or not. So let's put the values in, but we'll call it Q because we're not sure if these are equilibrium numbers or not. So the value for HOCl is 21 torr, and that value needs to be squared. And for water vapor, we have 200 torr given to us, and Cl2O is 49.8 torr. So it's time to use our calculator and see if this is equal to 0.09. So I take 21 and square it, then divide by the quantity of 200 times 49.8. Close out that denominator inside your parentheses. 0.044. So we see that Q is not equal to K. Q is less than K given these conditions. That means I need this number to get bigger, so I need my numerator to increase. That means if my numerator is to increase, then the pressure of my products must get bigger. So let's shift to the right towards products so that we can make my Q look more like K. In our other situation, we were given 1 atmosphere for each substance. So Kp is still 0.09. Let's evaluate Q. So I have HOCl is 1, and we square that value, divided by the water vapor, which is 1, and the dichlorine monoxide is also 1. So this makes for easy math, because Q is equal to 1. And that's way bigger than the K that we were given. So this is also not at equilibrium. Q is not less than K. Q is much greater than K. Silly me. And since Q is greater than K, that means I need to increase what's in the bottom so that my Q will go down. So we're going to shift towards reactants. And that direction we call left. Well, since nothing else was at equilibrium, I bet you can guess how this one's going to work out. But let's give it a try anyway. In this case, my my pressure of HOCl is 20.0 torr. Let's square that number. And then water vapor was 296 torr, and the dichlorine monoxide is 15 torr. So let's check with our calculator and see what values we get for this equilibrium quotient. So 20 gets squared, divide by, close out my denominator within the parentheses, 296 times 15, and seal up the denominator with my ending parentheses. How about that? 0.09, just as I thought. So under these circumstances, Q is 0.09, which gives us Q equal to K, and that means there's no shift, no net shift, because the reaction's already at equilibrium. We don't have to adjust the pressure of the products or the pressure of the reactants. So that's how we work with the reaction quotient. We'll be comparing Q to K anytime you're given values that it does not necessarily specify that we're at equilibrium or not, where we know what the equilibrium constant is and we're given values to compare. All right, we'll practice in class. See you soon.